Hello, and thank you for the invitation to speak here today. I've been doing DNS since the late 1980s, and I've been looking for ways to use DNS as a security tool since, I don't know, maybe the mid-2000s. And of course, GDPR in Europe and other similar privacy regulations around the world have come along and given us something to think about with regard to collecting passive DNS traffic, because so much of it can be used to identify a particular user, and there isn't really a good way to receive that user's permission. There's no signaling for that. And so what I want to talk about today is passive DNS, both in general and how it might sort of inform data science, but also specifically what can and perhaps ought to be done to avoid collecting personally identifiable information. Tagging this information with the identity of the user may make it more useful for some purposes, but that utility would come at a cost. So I'll talk more about that in a moment. And there's also a Q&A website where we can have a discussion about that if we run out of time now. So let me begin. So if the internet were a territory, then one map of that territory would, I guess, be the routing system with BGP and OSPF and all that, because if all you have is an IP address but no idea how to reach that IP address, then you're helpless. However, there's a much more important map of that territory, and that is the domain name system. Almost everything we do, almost every click of the mouse in a web browser, almost every command line command that we issue is going to cause one or more DNS requests to be transmitted. Now, this is not obvious because it's very fast. This is done many trillions of times per day, and the system has certainly had some high-profile failures. You'll read in the newspaper headlines that a certain website was down somewhere because some DNS problem occurred, or somebody was DDoSed and DNS was used as an amplifier for that DDoS attack. But those are exceptions that prove the rule. DNS is used all the time for everything, and we only hear about it failing or being abused periodically. And really, what I want to hammer home here is that if something is on the internet and it intends to be reached, I guess there's some small chance it could be a Tor server or something related to a blockchain or something else where you could receive the IP address of the peer server by some other means. But that's not the norm. Nothing beneficial or harmful will occur without DNS. That's a truism. When I say beneficial, I mean, things that you're doing on purpose, that you're doing. You're visiting a website, you're transmitting email, you're receiving email, the voluntary activities, but also involuntary ones. If you are being defrauded, if you're being taken to some lookalike website that appears to be your bank or your school or your credit card company, but isn't, and it is a clever forgery designed to induce you to enter your credentials, DNS will be as needed for the beneficial case as for the harmful one. And that turns out to be of great importance to those of us who are working on internet security at scale, because it means that if an attack has occurred, there's probably some trail of breadcrumbs in the domain name system to say what resources existed at the time of the attack, and perhaps to say what tags, what identifiers might be in common between those resources and other resources. Because if you can build an asset cloud fingerprint of your attacker and their resources, you might be able to do a better job of figuring out who they are. You might do a better job of predicting where they will strike next or how they will strike next. This is all called passive DNS. It's passive because we're not making queries. And I mentioned that trillions of times per day, queries are made by everybody. On the other hand, if a security researcher or law enforcement or investigative journalist makes a query at a time that is not during an attack, then that query might be a neon sign. It might be an indicator to the attacker that investigation has occurred. So in everything I'm going to tell you today, I'm going to be talking about how it is that we gather DNS transactions from the network, from cooperating server operators. And we're not going to be talking at all about how we make queries of our own, because in the case of passive, we literally never do that. I'm not saying that there aren't some non-passive DNS methods that could be of interest. I'm just not going to talk about those today. So I mentioned that this information has to be gathered from the network, and where it is gathered is servers, DNS servers. And there are essentially two kinds of DNS server, and I'll explain that in a moment. One of them is vastly more useful than the other for this type of work. But none of these servers will by itself see enough of the total DNS pattern space to gain any real insight into what's going on the internet. Now, clearly you can find out what's happening inside your university, inside your company, inside your ISP, maybe inside your smart home, by monitoring just the DNS traffic that is coming from inside your network. This is valid. This can be an important way to find out, for example, what botnet is active inside your network, because normally before a member of a botnet can contact its command and control server, it has to do some DNS lookups to go find that server. And a lot is done to obfuscate that lookup, right? The botnet creator does not want it to be easy for us to find them, but there will always be some characteristic lookup, and after a certain amount of effort, you can know what that will be. And so in those cases, I think PII doesn't really apply. If it's, let's say, me and my family, yeah, it could be that the people inside my house don't have a reasonable expectation of privacy. The same might be true for some companies. But in other cases, let's say with universities, it matters, and student privacy regulations would forbid that type of monitoring unless it was very carefully studied by the lawyers. But anyway, when it comes to DNS servers that are acting for third parties, let's say you're an ISP and you are serving a lot of customers, or you're a university and you wish to gather what can be gathered that is not a student privacy problem, what you'll find is there's nothing there that you can make use of until it has been shared and aggregated. And so one of my early works in the late 2000s was to create something called the Security Information Exchange, SIE, and some middleware and some protocols that allow that type of sharing to take place, because I want the utility. And since the utility does not appear until sharing and aggregation, that may explain some of what you've seen me do over the years. Now, of course, some DNS operators don't love and trust every other DNS operator. They might be a competitor. They might just be somebody, well, you don't know them, so you don't know what they'll do with the data. There's a lot that could happen. And that's why an intermediary is often needed. That's why the Security Information Exchange was created, but there are other intermediaries in the world who do this kind of thing. And again, this all tracks back to the fact that this information does not have its full utility until it has been shared and aggregated. So the two efforts that I've been part of, one is in the United States, it's called Farsight Security. And we do this for anybody, commercial, academic, nonprofit, law enforcement, whatever. Obviously, if you're a commercial user, then it's a commercial service. But if you're not, then it tends to just be something that we do for the greater good. In Europe, we had a situation develop around GDPR, which made it difficult for us as a US company to gather information in Europe and still respect the regulations. And so we created, with some partners there, a nonprofit company called Sie Europe. It's incorporated in Germany, and that does this same general type of work, but it doesn't do it commercially. So it has no products. You can't buy anything from it. It's just a way to put a little data in and get a lot of data out. And I'll come back to that in a moment. But that's the ecosystem of passive DNS. So this is a busy diagram because so much gets added to it over time, but the important part is those middle three clouds. At the bottom, you've got your stub resolver. That would be my laptop, your laptop, our smartphones, servers, virtual servers, any place where you might have a domain name but wish you had information to which that domain name currently points. So the traditional lookup there would be, gee, I've got www.something.com. I wish I had an IP address. I am going to go ask the DNS to bridge that gap for me. And then in that case, what's happening is you have a DNS question coming in at the bottom through the stub resolver, being transmitted to that full resolver, the recursive server. That's the middle diagram. And that, of course, is PII, because that has your IP address and a statement of your third-party intent. So that is the deepest, darkest kind of thing that GDPR and CCPA and so forth are designed to prevent the collection of and the data mining of. But in any case, if that recursive server has recently been asked the same question by some other local stub resolver, then you're going to get a very fast answer, and it'll come directly from cache on the left there. And, again, it'll be the same answer somebody else got. And I can tell you that there's some very popular names. www.google.com is in everybody's cache because there's always some local user who has recently asked that question. But if perchance you ask a question that isn't in cache, the answer is not in cache, then that recursive server has to go upstream to the authority servers. And that's where answers enter the system. And really, that's all you need to know for data science purposes about the DNS architecture. Questions come in at the bottom, answers come in at the top, they meet in the middle. Now, I do want to say some things have happened over on the left. DNS over HTTP has come about because of abuses by on-path actors, including the operators of these servers and the networks in between these servers. And so now it's become very popular to try to encrypt all of your DNS transactions and to transmit them to a faraway server with whom you probably have no contract, but in the way it is in the internet era, you probably trust them more than you trust your own ISP. Don't know why, but that is the way things are. So I have no more to say about DNS over HTTP today, except that some of the techniques that I'm going to describe in terms of passive DNS collection can be misused, and they can be done in a privacy-abusing way. And that is what has encouraged the creation of DNS over HTTP. That is why we, as data scientists, should think very carefully about what will be the institutional side effects of our operations. In other words, if we possibly can respect privacy, we always should, either because it might be the law or because we don't want to do harm that we don't intend, or because we don't want to be seen as probably doing harms that no one can really track to us. So this is deep water. Over on the right, you'll see two things that my team has done over the years. We've created a standard middleware protocol called DNS TAP so that a cooperating, participating name server can decide which telemetry it wishes to share, and that sharing will be in a very standard format. And so there are a lot of tools now for receiving that data. And of course, recursive servers all over the world are able now to speak. This is not an IETF protocol. DNS TAP is just sort of something we did, but it has become very popular. It's in bind, it's in unbound, it's in, all the open source name servers speak DNS TAP. I won't be talking about response policies today, but in any case, what you need to know for the purpose of today's remarks is that most of the PII that we want to avoid is below the recursive. It's between the stub and the recursive. And it turns out we don't need it. And let me explain. Now, if you're in Europe or anywhere in the European Economic Area and you want to join this, please go look it up on the web, sie-europe.net. Very simple process. Again, it's not a commercial company. It doesn't sell anything. It doesn't pay anything. It doesn't charge anything. So I feel like I'm okay making a pitch here because this is really a public benefit activity. And if you want to operate a sensor, then there are some things you need to know. And I'm going to tell you, even if you don't wish to operate a sensor, I want to explain this so that you'll understand what the thought process is by those who do operate sensors. So maybe the most important part of this is that this is not surveillance. Surveillance is observation that you hope people aren't catching you doing. That's not happening here. This requires deliberate participation and cooperation by a DNS server operator. Now, they may have some concerns about whether they are doing surveillance because maybe they don't have permission to install this software and send the data that they're sending. But from an overall process level, we know that somebody's cooperation is required. And so we're counting on that person to have obtained permission to do what they do. And we get our permission from them. And so there's sort of a chain of permission in the system. We don't collect any PII. So the thing I told you between the bottom and the middle, we don't look there. And it's all open source software. So you can inspect it and make sure it's doing only what you think it's doing. But pretty much you just install it, you configure it, and you forget about it. And it takes very little CPU or network time to do this. Now, one obstacle is that in most of the world, it's no longer fashionable to operate your own DNS server. In the early days, let's say the mid-90s, when we first started commercializing and privatizing the internet, everybody ran their own name server because that's just what everybody had to do. That was the only name server you had, was the one you ran. Then ISPs started doing it, then OpenDNS started doing it, then Google started doing it. And now we're, in this generation 2021, a lot of people have no idea that they could be running their own name server, either on their laptop or on a Raspberry Pi in their house, or, just put up a Linux virtual machine somewhere and run Unbound or Bind or something. Most people don't even know that that is an option. And they also don't understand why they should do it. What are they losing by not doing it? What can they gain by doing it? Well, one thing you can gain by doing it is have the ability to look at the traffic that is passing through it. Because if you just use some cloud name server somewhere, you have no idea what it's doing on your behalf. If you're running the name server yourself, that is insight that you can have. So certainly anyone with a test lab is running their own name server because they want to see what malware, for example, under test is doing, what lookups does it make, and what answers are received. But in any case, that thought process is something that everybody has been through before they decide to send data that you, as a data scientist, might get access to. And it will behoove us to remember that has taken place, because that gives us a certain burden of meeting their expectations. So what do you get? Here's a JSON dump. It's a little ugly, and I apologize for that. But it's better than raw hex, so that's fine. So generally, what you have is a timestamp. You have a source identifier, and that is the identity of the server operator. Then you have the actual message. And in this case, it's a query and response pair. Our sensor works in terms of query and response pairs. In other words, when we see a query, we don't put that in the telemetry stream. We just kind of keep it around in state, so that when a response comes, we can say, oh, the response came to the query that we've been hanging on to. And so once we have both the query and the response, then we can generate a message like this one. So you see the query IP, and that is the IP address of the recursive server. That's not the end user here. That's just that blob in the middle there. And the response IP is the authority server that gave us this answer. You can see it's UDP. We're gradually seeing more TCP, but UDP is pretty much responsible for most DNS traffic. Then you see the query port. So that's a UDP port number, and the response port is always 53 because that is the DNS service port. You have a query ID. That is a unique 16-bit nonce that is put into a query to help differentiate it from other queries that are in flight between the same endpoints at the same time. 16 bits is nowhere near enough, by the way. There's a lot of pollution attacks that rely on guessing that 16-bit number, and it's frightfully effective. So there are other ways to expand on that I won't describe today. QName is what was the question. And QClass is always IN for internet. Not sure what else it could be, but IN is all there is. A is just, this is the address. What we want is the address that goes with that QName. You can see the R code is that no error occurred. Had an error occurred, it would have appeared here. Now I've deleted some of the other details here because there just isn't room on the slide, and also doesn't really matter. But part of the response would have been, by the way, here's the address you were looking for. But as part of our message that our telemetry includes, you've got the query time in down to the nanosecond and the response time. And therefore, we know how long that took. So it's the delay, and we check the UDP checksum as one does. So this is the raw data. And I'm sure that any of you who have studied de-anonymization techniques can see that there's a lot here that is pretty dangerous. For example, if you know the recursive server ID, that helps you figure out which candidate individual was responsible for the underlying, not collected, but the underlying stub transaction. Since, let's say you've narrowed something else down to 3 candidates, and they each use a different name server, you can tell from this which candidate was responsible because you know which name server was responsible. The query port is also interesting. If you've got NetFlow, you can often use the query port to narrow down who the end user was. That query time is amazingly useful because, you know, it might have taken a little bit of time for the question to get from the stub to the recursive. But if you've got good NetFlow or good packet traces in general, then knowing the time at which the query left the recursive server will help you narrow down which candidate end user was probably responsible for the underlying cache miss. So in other words, this is dangerous as hell. And if you are in possession of it, you have a really mightily high standard of care. And we practice that care. And one of the things that we do is we strip most of that out. This is what this kind of thing looks like once it has been through our filtering process. We have a deduplication process. We do all this in real time, which is interesting. So that's a fun type of programming. Reminds us of when a Z80 was considered fast and 64K was considered a lot. You don't have a lot of time to do what you got to do if you're looking at 300 and some thousand of these events per second. But we do. And so I'll tell you, just let me focus your attention on that count. So what we've done here is to gather everything into a tuple, and we can see that the time first was at 2:49. It's UTC, so in the second hour of UTC, and the last scene was in the 18th hour. So it's about a 16-hour or so time window. And we're now saying this window is closing. This is an expiration event for the dedupe cache. And we saw this pattern 48 times during that interval. And so gone is the query ID, that 16-bit thing that isn't long enough. Gone is the UDP port number that helps you disambiguate using NetFlow. Gone is the server ID, the sensor ID. Gone is the individual nanosecond granularity timestamp. What you're left with here doesn't help you at all to understand who the end user was. All you've got now is some indication of what part of the DNS pattern space was accessed. And that's how we like it, because there's a huge amount you can do with this. I'll give you a short demonstration in a moment. But there's a huge amount you can't do with this, most of which is illegal somewhere and probably immoral elsewhere. So first thing to do is not collect that PII data. And then second, from what you do collect, compress the heck out of it so that there is so little left that the valid data science uses that you wish to make are not violating anybody's privacy. Now, no anonymization technique is perfect. De-anonymization is both a science and an art. It is something that is practiced commercially at scale, probably also practiced by law enforcement or national security entities or whatever. So trying to put the puzzle back together when half the pieces have been taken from you is something that everyone on this call has had to do. And obviously I advise you to think carefully about what the implications will be before you do it. But I'll just give you an example of something that is done to avoid all of the work I just told you we do. And that is that you just have to pick some random looking string and connect it to some part of the DNS tree. In this case, it's going to .akamai.hd.net. And then you just issue, a CNAME is basically an alias. What this is telling you is that a question for that first name should be treated as though it's a question for the second name. And as soon as you hear that second name, you know that the question was asked. And if this is a string that you only gave to one user, let's say as part of an advertising cookie or an image token or image tag or something like that, then from this, you know that the question had to come from that. So you don't need to know necessarily what their IP address is to be able to know that the thing you handed out has been consumed. And if you look at that in timeline order, you're going to be able to correlate it to other things that the same entity did. Now, there's another things also coming from akamai.hd.net, where what you know is you do know their IP address and you know which name server they use, because you've already figured that out from previous state keeping. And now you have something with a specific timestamp. And you can see that the target of this is .cname.client2ns.com. This is, I don't know, disambiguation, sorry, long day, at scale. And, Akamai is not violating people's privacy. They do this because they have to run a global content delivery network, and they need to know this stuff in order to balance the forces. They've got mighty forces and they have to balance them. But there's a huge amount of this that gets done for less respectable reasons. Sometimes it's because you really want to know who that investigative journalist is, and you find a way to feed them something through their web browser that will cause them to out themselves via the DNS protocol. There are a lot of other things you might do. You can imagine how this could be abused in surveillance capitalism, for example. And it is those abuses which I think drove the creation of the GDPR in Europe and the CCPA in California. So what I'm trying to describe to you is that no matter what you do, there will still be people who are doing things designed to pierce the veil that you have placed. I would advise you don't be one of those people, but I would also advise you be careful, because something that you did that you thought was going to be harmless because you did all that anonymization might still be harmful because of this de-anonymization, this style of de-anonymization. We tend to filter this stuff out as part of our real-time process. So every time we find something else that could be this, we just say, okay, don't let that through. Okay, so I wanted to show you a couple of use cases. And in this case, I'm going to use the passive DNS database rather than showing you more real-time. The real-time tends to scroll off the screen too fast for this type of presentation. So I want to explain that the first thing you get to do if you have a record of all those cache misses, of all those tuples with the start time and the end time in the count, is you can have a time machine. You can have it be that if maybe the answer you would get from DNS, if you were willing to make an active query, which you're not, today is different from the one that the victim got yesterday. If, let's say, you're looking into a crime or some other kind of abuse that was perpetrated, and so you know what the victim did. What you want to know is, what did the victim see? What happened? So this is a time machine. It's a time series database. You can look backward, and that's cool. But you can also do some pivots where I mentioned you might want to find out who is the actor, even though they've hidden their who is and they've hidden everything else. They're doing the best they can to use a bunch of resources that are in no way traceable to themselves. They're probably still traceable to each other. In other words, some of their resources are going to be using the same indicator as other of their resources. And while you don't necessarily know from that forensic fingerprint who the actor was, you will know if you see them again, and that's huge. And then you can also do a certain amount of survey work, which I call looking at online neighborhoods. So I'm going to switch applications to a terminal window, because that is my happy place. So let's do this. Let's say, oh, hey, I think I have something in my cut buffer that'll work here. No, I don't. Oh my goodness, all right. So let's just ask the database for the ODSC mail servers. And the database that I'm using and that my company provides and that Sie Europe has a free copy of is not ordered. So I'm going to tell the client, by the way, please order the responses in reverse time order. So what you're seeing now is a history of how ODSC has been handling their own email. So in olden times, which is 2011 January, our database starts in 2010. So this is, almost as old as it gets for us. They were using secureserver.net, which I think is an anti-spam service of some kind. They did that for about 5 years. And then they said, we think we want to host our own email, and we're going to call that mail server mail.odsc.org. They did that for about a year and a half. And then they eventually said, it's crazy to use a separate name like mail. We don't need that. We can just point ODSC.org's mail at a server. ODSC.org will have an address record. And they've been doing that for the last 2 years, 61 days. Now, ODSC is not a criminal, but this does help you understand the value of the time machine here, Because if you do a live lookup, which I'm willing to do, MX, there we go. You know, all you're going to get is the current value. So what you're seeing here is that odsc.org is the current value. If you want to know the history, there's a way. But here's something else. We've learned an IP address. So let's take a look at that. Oh my goodness, look at all that stuff. So what you just saw, scrolling by too fast to read, is a time-ordered set of all of the names that have ever pointed at that address. And so what you know from this is that ODSC's email service is sharing this resource. This is a shared server somewhere, or a load balancer of some kind. And so there's some things in here from Dataforce, IRCCI, CA Hunter Education, Greyhound. So again, they're not a criminal, but if they were, you would sure love to know who they are sharing this resource with. Now, sorry. I guess I'll do one last thing, and that's the survey that I told you about. So in this case, I'm going to ask for the surrounding network, which will be a class C, which is modernly referred to as a /24, because we all went classless. So now you're seeing all of the other, any name that points at any address in the surrounding class C network. So this is what I mentioned as a survey possibility. So this is not directly sharing phase, not the same IP address, but it's very nearby in the address space. And so you know that these people and ODSC are probably buying services through the same ISP. And again, if they were criminals, that would be huge to know. So I hope that that explains a little bit of how this can be useful. There's a lot of machine learning now that goes on as part of law enforcement or as part of commercial security work. And so this data is going into an awful lot of wood chippers. And so it is being used. It's probably not being used by all of you. I hope that you will give some thought to that. Again, if your purpose is not commercial, you don't have to pay. So this is not me trying to sell something to you. This is me telling you DNS is really useful for the type of work that we do and that I think you do. And most importantly, please, as you contemplate a supply chain to support that effort, keep track of what permission you have to see what you're seeing, and do everything in your power to avoid collecting something that you don't need and to have permission for everything that you collect. So I've given some URLs here. Some of this is open source software. Some of this is other open source artifacts like Farsight Labs, Sie Europe. DNS TAP, I mentioned, is the telemetry middleware and protocol that is used for this type of collection. And there's a tech report there on the sensor itself. And so we have a few minutes that we can use for questions. And I guess I encourage that. In the absence of questions, I will turn the microphone over to the moderator.